Okay, this is recording. So today I'm gonna so, so today I'm gonna derive the governing equations for the linear elasticity. And so what we have so far from the previous lecture is we have the these four six equation beforehand, and we derive from the mass balance, the linear momentum balance, the angular momentum balance, and the free energy imbalance, and we apply the Coleman-Noble procedure. So let's get through these steps. So first, we just know that the mass is balanced, and we have the linear momentum balance, this equation, and in the lecture, we change the variable to work with the TRR, or the second periodic stretch, because uh, when we reach the point that we have to apply the PMFI, we will see that the first periodic stress is neither the frame indifference or the frame invariance. So it's easier to work with the TRR. And the TRR is also the power conjugate with the material derivative of the Cauchy green tensor. So we choose to work with this 1, 2, 3, and 4 equations here. Okay. So after we have all these 4 equations, we have to apply the Coleman-Noble procedure, and we can see that uh, these first 3 equations don't give any info or any more constraints. Uh, so we have this one that gives us a constraint. So we know that this equation. So if we ignore the local dissipation function, so we have this one less than 0. Okay, less than or equal to 0. And then so we choose to work with this. We choose to work with these variables, and so we define that the free energy is the function of C, and the TRR is also the function of C. And this also satisfies the principle of material frame indifference, because we want to ensure that the material property shouldn't depend on the observation frame, like whether or not you see the same material and you are see with the there are some different persons see this material, the response should be the same and should not be varied. So we have this one, and after that we know that from this one we can take the material derivative to get this one, and so we substitute the material derivative of the free energy in the reference configuration back in the sorry in the fourth equation. So we're gonna have this one, this equation, and this equation have to satisfy the inequality. So we can force the C to be 0, always 0, because C dot is arbitrary. So the only way we can do to satisfy this inequality, so we have to make this one equal to 0. And after we like simplify the equations, we got the equation number 6, which basically the hyperelastic, for the hyperelastic material. So this is the recap, and I'm gonna develop to the 3 governing equations for the linear elasticity. So let me see my notes. Okay, so for the first step, so this step is has mentioned in the lecture, in the previous lecture also, but I'm gonna restate it again. So for the linear elasticity, so we have 2 assumptions. Okay, so we have two assumptions. The first, okay, assumption. So the first one is the reference configuration is natural. Okay, the reference configuration is natural. In other words, it is stress-free. What does it mean? So the reference configuration is natural if it gives local minimum of the free energy. So free energy. This one. Okay. So for arbitrary C, we can write that the free energy function for arbitrary C should be greater than or equal to the function of free energy if the C equal to identity tensor. So the only, like, if the C is like equal to 1, so it's equal, and any other than that, it's gonna be like greater than the C when the C is the identity, okay, in uniform state. So, and we define this one, okay, we can have this one as to be 0. So this is the, like, the, it's like the least free energy, okay, and, but we also state that if it gives local minimum of free energy. So to identify the local minimum, we know that from the undergrad level mathematics, we have to take the partial derivative of this function with respect to C, and evaluate as C equal to identity, and we have to get the 0 because it is the local minimum. Okay, so now we have, okay, now we have these two information, and from equation number 6, so we have to scroll back a little bit. So this one, okay, this one, we can evaluate the TRR when C is equal to identity. So C is equal to 1, basically. So the TRR, okay, this one, partial derivative of free energy with respect to the C, that's C equal to 1. So we know that this one is equal to 0, right, from this one. So we have that TRR is 0. So if TRR is 0, then we can write that. So the first PLR curve and the Cauchy stress tensor is also be 0. So basically, the first assumption is the reference configuration is natural, or this is stress-free. Okay. So this is the first assumption, and the second one. The second one is the deformation. So the second one is deformation consists of small displacement. Okay, from the reference configuration. Okay, so we look at this. So we said that this one should have a small displacement, and the small displacement, so we look at the definition of the displacement is like u, okay, is equal to small x minus big X, just like that. And we know that the deformation gradient H is basically just the gradient of the deformation and of the displacement, sorry. And we know that the deformation gradient is 1 plus the displacement gradient, and the right Cauchy-Green tensor is F transpose dotted with F. And from this one, we also know that the Lagrangian strain or the strain with respect to the reference configuration E is equal to 1 over 2 C minus identity. And we just use this useful identity, useful information here up there to have this one. So it basically is just like, okay, so the first one is the F transpose, right? So we have 1 plus H transpose. So we distributed the transpose into the parentheses. And on the right one, we have 1 plus H, and we have minus 1. So basically, we're going to have the, after we multiply it, we have this one. Okay. And for the small deformation, so what is a small deformation? So we take that, the magnitude of H reach 0. So we're going to have this one as 1 over 2 H plus H transpose plus the little o of the terms that relatively small, smaller than the H. So it's just the higher order term. So we can write that for the small deformation that have the small displacement, we can just say that the strain is just 1 over 2 times H of the displacement gradient plus transpose of the displacement gradient. Okay, this is a second assumption. This one can be called the infinitesimal Lagrangian strain tensor. Okay, so now we have the assumption for the linear elasticity. So we can build and develop the Governing equation up on here by using the equations from the previous lecture and these assumptions. So we can go on. Okay, so let's get back to what we have. So we know that we're going to have the function of the free energy and the function of the TRR, right? So we're going to estimate these two functions. Okay. So we're going to estimate for stress for the TRR and free energy. Okay, so the first one, we're going to estimate the stress first. And how do we do that? Again, so we take the Taylor series expansion to that function. So we're going to take the Taylor series expansion for the TRR at C equal to 1, around C equal to 1. So we're going to have T, like the function TRR, which is the function of C, will be equal to the partial derivative of the TRR, this function itself, with respect to the C evaluated at C equal to 1 times C minus 1 plus the higher order term, or the little o of the absolute C minus 1. So just magnitude, okay? And once we get here, we're going to introduce what we call the elasticity tensor. So we have to know that, so by definition, the elasticity tensor is the C, okay, like the very big C, equal to 2 partial derivative of the function TRR with respect to the C at C equal to 1. Okay, so once we know that this is, by definition, is the elasticity tensor, and we see that it's quite look really similar. So we can write this expression again with including the elasticity tensor. So we're going to have C equal to 1 over 2 times the elasticity tensor, so 2 cancel out, right? And times C minus identity. And again, we carry that little o to this expression 2, and as C reached 1. So we estimate around C equal to 1, right? Like C reached 1. So we're gonna have, so we can neglect the higher order term, but before we can do that, or before we do that, we can like simplify a little more, because we see that 1.5 times C minus 1 is just the strain tensor, the Lagrangian strain tensor. So we can write it like this too. So this one is just scalar. So C dotted with E. Okay. And as we neglect the higher order terms, so okay, so we can just carry on like the little o of this E as E reach 0. So if we neglect the higher order term, we're gonna neglect the like what we can neglect, okay? Because the small deformation assumption, so we're gonna have the TRR equal to the elasticity tensor times the strain tensor, Lagrangian strain tensor. And we know that from the that we apply the CNP and PMFI. So this is just basically just a TRR. Okay, so this one is the estimation of the stress, okay, by using the Taylor series expansion. So I'm just gonna give that. So this one is equation 7. This one is equation 8. All right. So the next one, we estimate the stress. Already estimated the stress. Now we're gonna estimating the free energy. Estimate the free energy. So again, we take the Taylor series expansion. Okay, we apply the Taylor series to the free energy function about C equal to identity. Again, just the same process that we did for the stress. So now we have function of free energy, and so we just approximate about C equal to 1, right? So we can just basically write the first term as the free energy function, where C equal to 1 plus C minus 1 double dot with the partial derivative of the free energy function with respect to the C, evaluated as C equal to 1 plus 1 over 2 C minus 1 minus identity double dot with the double partial derivative of the free energy with respect to the C twice, as C equal to 1 times C minus 1 plus, so just move it a little to the left. There's some room on the right here. And then a little o of the higher order terms of the C minus identity. All right. So this one looked big and it's like a mess if we don't know any information beforehand. So luckily, we know that from the assumptions one. So how could we can take the advantage of what we have before? So we scroll down or scroll up to the assumption number 1. We see that we just define the free energy when C is equal to 1 to be 0. And that partial derivative is also equal to 0 when evaluate as C equal to 1. So now we know that these terms and this term is going to be 0 by the first assumption. All right. And this one is going to be something else. So I will start from the equation number 6. Where is the equation number 6? So this one. So the equation number 6. So we have that the TRR is equal to 2 times the partial derivative of the free energy function respected to C. And from the 7, we know that the elasticity tensor have something with the TRR too. And okay, let me just write this up here. That TRR is the TRR function of C. And then, okay, I just note that this is one from 6. And from 7, we know that the elasticity tensor is 2 partial derivative of the TRR C respect to C as C equal to 1. And just highlight, okay, this one we can substitute to this one. So now we're going to have that. So the 2 is just a scalar. We can pull that out in the front. So we have 4 double partial derivative of the free energy function with respect to the C twice. Okay. Equal to the elasticity tensor. So we can have that just pull the 4 down here, we can have that the right-hand side is going to equal to the elasticity tensor over 4. Sorry, this one is tensor. And now we can substitute this back in there. Okay, so now the free energy function, the estimation of that is going to be like really nice. So we can write the free energy function is equal to the terms before the 1 over 2 here is just 0 because by the first assumption. And it leaves that this one is have 1 over 2, we have 1 over 4, which is a scalar. We can pull that out here. It's 1 over 8 times c minus 1 times, double dotted with the elasticity tensor because we just substitute this by this, okay? And times with the c minus 1 plus the letter O of the c minus 1 magnitude squared. All right. Okay. And again, if we neglect the higher order terms, and we can see that there is like the tensor, the E tensor, the Lagrangian strain tensor, like behind there. So we can rewrite it like 1 and 1 over 2 times 1 over 2 c minus 1 double dot with c times with 1 over 2. So it's basically just a scalar, so we can factor back. Little o c minus 1 square. Okay, so I just neglect the higher order terms, and it leaves 1 over 2. This one is just the Lagrangian strain tensor times c, no, not c, times the elasticity tensor, double dotted with elasticity tensor, and times with E. So this one is the free energy estimation. So I give that equation number 9. Okay, so we got here equation number 9 so far, and I would like to step back a little, that we can see that this information not only simplify the estimation of the free energy, but it also gives us that the so let's just look at this one. So it also gives us the another information that the elasticity tensor is symmetry, in the sense that if we can write it as the index notation. So this one can be respect to Cij, and again with Ckl. So basically, like the elasticity center tensor Ijkl is also equal to the Kl Ij, because these two can commute in the partial derivative, right? So this one is the another important properties of the elasticity tensor. And we also have 2 more properties, but I'm just gonna skip that because I may not have enough time. But the another 2 is basically just like the elasticity tensor is the positive and semi-definite, and the other one is just like obey in the in the symmetry transformation that C can be in the middle of the parentheses and can be pulled out. So it's just another properties that we could know that. Okay. And after we got this, so now we have the estimation for the stress and for the free energy. So now we can assemble it and get the last three governing equations that we would like to have it. Okay, but before we wrap this up, we have a lot of variable that is like some of them is like the TR, just like in the reference configuration, in the current configuration, and like we can just like simplify it and understand that it is the same. Okay, so we can start it with so we have, okay, just put a line out there. So we have the Jacobian, which is the determinant of the deformation gradient. And from the first assumption, we know that the F is going to be something like the identity matrix with the some terms that negligibly small compared to one. And if we, so basically we just can imagine that. So we have the identity matrix. And if we just take the determinant of that, we can just have one, right? But we can include that we have some small terms from the small terms in each component of the F. And so when it like we have like that, so the inverse of the J, this can also be it can also be the one plus the little o1 here, because it's just basically like close to the identity matrix, the same identity matrix. So we can have this one. And for the Cauchy stress tensor, we have the definition that is equal to J inverse times the F times the second Pure Kirchhoff and F transpose. So we basically have the one. Okay, so I would like to like in my understanding, it's easier to look this way. So we just have the one times the identity times the TRR and times the identity transpose. So it's just identity. So it's basically like we have T is equal to TRR. And again, if we apply to the first Pure curve from Jacobian times the Cauchy stress tensor times the F inward transpose. So we're going to have the same thing. So we have one here, we have the Cauchy stress tensor here, and we have the identity matrix here. And we're going to have that TR is equal to T. So basically we have like TRR is equal to TR is equal to T. Basically, just like that. And just note that this one valid for the small deformation because we assume. So we just like, if we don't assume, we cannot like have this statement here. Okay, so we have to keep in mind that this one is from the assumption that this material undergoes the small deformation. And there are also other two variables that can can be defined too. So from the like, if you go back to the mass conservation, we have that like rho r is equal to j times the rho, right? So the j is basically one, right? So it just like right like this, and it goes the same way with the conventional body force, which is like I can write it like the BR as we have in the previous lecture. is also equal to B in the current configuration. So after we have all of this one, we can go to the last step, which is we have to introduce we have to note that the elasticity tensor, sorry for that pronunciation, is the isotropic function. So we know that, we don't know that, but the Gordon-Fried and Anand says that C, the elasticity tensor times the E, is equal to 2 mu times E plus the lambda times the trace of E times the identity matrix. So this one is the definition of the C times the E if it is isotropic. And these two constant is called the Lame constants. Okay, so now we can assemble all the things that we have done before to write the first governing equation. So the first governing equation, okay, we have to go back to the equation number 8. So from this one, we have that TRR is equal to elasticity tensor times the E, the Lagrangian strain tensor. And we know that TRR is also equal to the T, right? That we derived before, just a second ago. So we can write that T, the Cauchy stress tensor, is equal to C, the elasticity tensor times the Lagrangian strain tensor, and from the isotropic definition, we can write it down as T is equal to 2 mu times E plus lambda times the trace of E times the identity. And this is the first going equation. All right. And this one is basically just give us the information of the stress-strain relation for the linearly elastic isotropic material, okay? And the second one is from the equation number 9. So the first one is basically just comes from the estimation of the stress. And the second one is comes from the estimation of the free energy, this one. So we can write that as free energy is equal to 1/2 times E double dot with the elasticity tensor times E. And we can substitute the C times E again, such that we have E times the 2 mu E plus lambda times the trace of E and the identity matrix here, just like that. And we distribute the E double dot into the parentheses. So we now have the first one is just, okay, so 2 cancel out. This one will be cancel out and leave the mu, right? And we have E double dotted with E. And the second one is 1.5 times the lambda, because it's just a scalar, we can pull it out, and we have E double dotted with the trace of E times with the identity. Okay. And so by the definition, this one is just the magnitude of E squared plus 1 over 2 lambda, no. So these terms is going to be the trace of E squared. So now we have the second governing equation like this. Okay. So this one is the free energy that have to satisfy the inequality. So this is the second governing equation. And the last one, the third governing equation. The third governing equations comes from back into the second equation. So just like the linear momentum balance, but we can just use this form. It's okay as well because it's the same. We just change the variable. But now we know that the rho r is just can be right just as rho, tr is just can be t, and the br can be just b, right? So we can write it again as the rho. Okay, I just rewrite it, the whole thing first. Divergence of the first Villa-Kirchhoff plus the body force in the reference configuration. And we also know that the displacement is the little x minus the big X. And we can write that the small x is just the displacement plus plus the big X. And if we take the material derivative twice, this one is like constant, right? So we can write it as this one too. So we can write it with the rho r can be just rho. And in the terms of displacement, we can write in the terms of displacement as the u double dot. Okay. And equal to divergence of the t plus the body force. And we can substitute t from the first governing equation, and we can substitute by write it down as the divergence of the 2 mu e plus lambda times trace of e times the identity matrix plus the body forces. And then we can take the, so I just distributed divergence into the parentheses and I can do it one by one. So the first one is the 2 mu is going to be the partial derivative of the E. So E is basically just like, we can write it as a function of the displacement. So it's just the partial derivative of ui over xj plus uj over xi. So it's just a transpose, right? Okay. And so this one gonna have the ij component. So we have to partial derivative with respect to the j. All right. And the next one is we can pull the lambda out there and we can take the partial derivative like the first one. So it's just a divergence, right? And it is the trace of E, trace of E. So I just can basically just like, the trace of E is like the partial derivative of the partial derivative of uk with respect to the xk and the delta ij plus b. So like so we just leave it like so it just kind of mix, and we can see that the two is cancel out, so it leaves mu and terms with the partial derivative of ui square with respect to the xj square plus partial derivative of uj square like twice, and we have the respect to the x and xj over there. And for the trace of e, so if I just contract on j, I can have wait a minute. Okay, I can. So this one is going to be 1. So I just contract it, and it's going to be the partial derivative of the uk twice with respect to the xi, and because I contract with j, right, and xk plus the b. Okay. So if I write it properly, it's just like xj is occurs twice. So it's just a summation. So we know that all of these are the components of I. Okay. So and the j and the k is just the dummy in the indices. So I can just write it again as this one. So the partial derivative of the uj ui respected to xj plus, because this one, the j and the k is just the dummy indices, right? So it can be like whatever, it can be L, can be M, can be N, but it just leave it as j. So we have the first term and the mu, and the second term is lambda times the partial derivative of uj twice with respect to the xi and the xj plus the b with the ith component. So as we reach this, we can have the displacement equation of motion. So we can leave it right there, or we can make it more tidy, because we know that it had a Laplace operation, which is the equal to the gradient twice. So we can and this is the we take the gradient twice, right? So we can write it as the mu and Laplace of the u plus the mu plus lambda, and this one is basically the gradient outside and the divergence. So gradient inside, gradient freedom. Just I think just look like this times the divergence of u plus b. Okay. And on the left hand side, we have this one. Okay. So let me check if all of these three is correct. Okay. So this one. So this one is correct. And the free energy is mu E squared plus 1 over 2 lambda trace of E square, correct? I think the first one is also correct. So that's it. So now we derive the linear elasticity equations, which consists of three governing equations from the like mass balance, linear momentum balance, angular momentum balance, and the free energy imbalance, with ignoring the energy conservation. And we apply the Coleman-Noble procedure and have to make sure that it is also satisfy the PMFI, and we choose to work with the symmetric stress to like have a less mathematical exhausting. And we apply the assumption that the reference configuration is stress-free or is natural and undergoes in the small deformation or small displacement. And then we estimate the stress function that we have from the CNP and the PMFI by applying the Taylor series expansion, and we got the this one, the equations number 8, and we do that again with the we do that again with the free energy function. So take Taylor series again, and we gather all the information beforehand to simplify and make it neat, and have this nice little equations number 9 here. And we can also change that, and we can also see that there's some like interchangeable of the variable between the current configuration and reference configuration that we can substitute back to the equations before that to get the governing equation. And most importantly, we have to know that the C, the elasticity times this Lagrangian strain tensor, if it is isotropic, it's gonna look like this. It's gonna look like this. And after that, we just mix it up with like assemble all the equations that we have, and we have the stress strain relation, and we know that what is the function of the free energy, and we now have the displacement equation of motion for the linear elasticity. And I think that's all. Thank you so much.